Yeah, so you guys should have received now the notification of the recording. So in this second period, we will be together studying the very nice topic of inorganic chemistry. So basically, our main objectives or our goals during this course and during this period is using or motivated by the diverse and fascinating and interesting and powerful subject of inorganic chemistry, we will try to understand several properties of main classes of elements and compounds. With this, the idea is to develop then the foundation in terms of a structure and reactivity that governs several systems that are described by inorganic chemistry. We will try, based on these foundations, to unravel the impact of inorganic chemistry in our life, in our industry, in order to tackle global challenges in areas such as catalysis, photocatalysis, development of sensors, for example. And with this, we aim that with this knowledge and these concepts of inorganic chemistry, we can then excel at applying inorganic chemistry or applying or knowing how to apply what we learn and see how inorganic chemistry is such a fascinating topic and how inorganic chemistry can be put towards to address current global challenges. Of course, I am a professor of inorganic chemistry and I like inorganic chemistry very much. So maybe I have like a little bias saying this, but to me, inorganic chemistry is one of the most fascinating areas of chemistry, and with inorganic chemistry, we can truly address the main challenges that our world currently faces. I would say that inorganic chemistry, it is at the forefront of many disciplines, and it is at the core of solving several challenges that our world faces today, such as global warming and climate change, for example. So going more specifically, our course will be divided into three main parts. So we will be discussing in the first part, the chemistry of the elements. So here we will be discussing atomic properties and periodic trends, which we will start on this today. Then we will discuss acids and bases, oxidation and reduction properties, common form of several elements in the environment, and how this can be put towards methodologies for the extraction and isolation of these elements. Then, in the second part of the course, we will focus on solid state chemistry, in which inorganic chemistry plays a major part. So therefore, we will discuss chemical bonds in solid compounds. We will discuss structure types. We will discuss lattice energies. We will discuss defects and how these defects in solids are very important. And also we will discuss several examples in terms of synthesis and applications in the field of materials chemistry, which overlaps with inorganic chemistry as well in this area. Finally, in the third part of our course, we will focus on coordination compounds, which is a very important class of molecules widely employed in industry as well as homogeneous catalysts, for example. So we will discuss the structure of several coordinating compounds, how are their naming convention. We will discuss isomerism and bonding in these materials. We will talk about reaction mechanisms with respect to the synthesis and reactions that these coordinations compound undergo, and also in terms of reactions mechanisms in which these inorganic compounds are applied as catalysts for important industrial processes, and then we will finish with a discussion on organometallic chemistry, which is a very important class of coordination compounds in which we can observe a direct bond between a metal and carbon. So in general, these are the main books that I will be following during the course. But I would say that Inorganic Chemistry by Shriver, the edition number 6, will be the main book that I will be following. So if you guys want to study by yourselves or have extra study material, this is the book that I recommend. I believe you have easy access to this book in the library. But of course, the older version, which is the 5th edition, is always good. And then any other books like these ones dealing with inorganic chemistry are also okay. But to let you know, most of the material and most of the things that I will be using and covering I will be mostly based on inorganic chemistry by Shriver. Regarding your grades at the end of this course, which is a very important topic. So this will be based on an exam and also on the homeworks. So every couple of lectures, for example, or every week, more or less, I will try to give you guys a homework, and then I will give you some time for you guys to complete this homework and then turn it in to me by email, for example. So like turning in and completing the homeworks will be 20% of the grades, and the exam will be the other 80%. I do this because I believe that a major part of the learning is learning by doing. So I think that if you guys do the homeworks by yourselves and work on it, I think this is a great way to learn inorganic chemistry. And then if you do everything, I would be happy to give you 20% of the grade already based on the homeworks. So I highly recommend that everybody does all the homeworks and turning in time, so you can get already 20% of the grade. So inorganic chemistry, in this course, one of the things that we will be doing in this lecture and also in the first part of this course, I can say, is to have a journey across the different parts of the periodic table. So we will explore, study, and understand and travel around the periodic table, which is like one of the amazing achievements in terms of the history of chemistry. So today, we will start with this journey across inorganic chemistry and across the periodic table by starting to discuss some periodic trends or trends along the periodic table. Then we will focus on the description of several atomic properties across the periodic table, such as atomic and ionic radii, ionization energy, electron affinity, electronegativity, polarizability, occurrence, metallic character, oxidation states. Then we will switch to the description of compounds, or how these periodic trends affect elements in compounds. So we will discuss like trends in terms of coordination numbers, bond enthalpies, and also some of the main binary compounds for several elements. And then we will finish this discussion by focusing or describing the reasons why the first member of each group has markedly like different properties relative to the other elements of the group. So this is called the anomalous nature of the first member of each group. So in our lecture today, the goal is to cover all these topics. So the periodic trends and the atomic properties. But let's see how we go. All right, so let's start then with the atomic properties and periodic trends, as I mentioned. All right, so the periodic table is one of the great achievements in the history of chemistry because it provides a very simple, very direct, and very effective way to organize the elements. So it provides an organizing principle that enables us to coordinate and rationalize the several physical and chemical properties of the elements. So this is very useful for the prediction and rationalization of different types of properties. And based on where the element is located, we can predict these properties based on this organizing principle of the periodic table. So when we mention the concept of periodicity, this means the regular manner in which the physical and chemical properties of the elements vary with the atomic number. And the periodic table, therefore, has the elements organizing by increasing by the increase in their specific atomic number. So we will summarize some of the trends in these physical and chemical properties across the periodic table and interpret them in this in our lecture today. All right, so this is the main organization of the periodic table. So here the periodic table is organized in different groups, right, which are the columns or the way that the elements are organized in the different columns, and also into different periods. There are the different rows of this periodic table. So here, so for example, these groups and periods are organized into into numbers with increasing number as we go across the group or across the period. So this is, for example, from left to right, period 1, period 2, 3, 4, 5, and so on. And then group 1, 2, 3, 4, 5 for the columns, and then for the rows, the same thing. So here we have the hydrogen, right, which is not shown here. So this is period 2, period 3, period 4, period 5, 6, and so on. So the elements in the first group are called alkali metals. Second group, alkaline earth metals. The elements in this region are called transition metals, which this represents the D block, right? We also, here the elements in group 16 are called chalcogens, in 17 halogens, and on 18 noble gases. So these are like some representative names that of the elements of the different groups. That the different groups are called. Also, these kind of groups are approached as the main groups of the periodic table because they represent the S and the P block, which means that their electronic configuration or the valence electrons is in an S orbital or a P orbital. And here we have the transition metals that have configuration, electron configuration in which the valence electron occupies a D orbital. And we also have inside here the transition metals, the F block as well. Okay, so are these concepts too easy? Is this familiar to everybody? Okay, let me check the chat. Okay, all right. I am starting slow, but it should pick up soon, like the complexity of everything. But anyways, if are you prepare a feedback system on Moodle after this class, and then you guys can let me know, or after every class, so that you guys can let me know about the rhythm, like if I'm going too slow or if I'm going too fast, or and so on, so that I can adjust the speed. But this is an introductory, like the first lecture, so it will start a little easy today, but then it's gonna get harder later. And harder, like, means not so difficult, but challenging and exciting. All right. So talking about the valence electron configuration. So the valence electron configuration of an element can be inferred for the group number, where N is the period number. So for elements of the group 1, the electron configuration ends in NS1, 2, NS2, 13, NS2, NP1. And here we have like 3 electrons in the outermost energy level: 14.4, 15.5, 16.6, 17.7, 18.8. And then N here refers to the period number. All right. So the electron, so this is the valence electron configuration for the elements in the different parts of the periodic table. So here, S for group 1, 2s, 3s. So here is 2s1, 2s1 here, 2s2, and then 3s, 4s, 5s as the periods go on. The same here, the same thing for the P block. So 2p in this period, the third period 3p, and so on. And the same thing for the D block and for the F block. And then we can use this Aufbau principle to arrive at the electron configuration or the valence electron configuration of each element, filling up the orbitals in this kind of sequence and order as shown here in this diagram. So for example, what is the valence electron configuration for argon having atomic number 18? So please help me. So argon is here. So it's period 3, group 18, period 3. So it should end here, right? And it should have 8 electrons in the valence level, right? So this would be the configuration, right? Is that clear to everybody? 2, 6, 2, and 6, right? Okay, very easy. So this is for the S and P block. I mentioned that this is also for the D and the F block. So, okay, so looking at the D block, so the electron configuration in the D block is slightly less systematic, because in this case, it involves the filling of the D orbitals, and this refers to the D orbitals with n-1 instead of n for the period. So if we consider period 4, this means, for example, in the group 3, 4s2, 3d1. So we are the d orbitals that are filled are the d orbitals of n-1, where n is the period. And here we are talking about the period 4. So for an element in group 6 is 4s1, 3d5. Okay, but this case specifically, this occurs because the atoms or the elements generally have, they reach a state of increased stability if the orbitals are totally filled or totally half filled. So that's why for this group 6, for example, we have the configuration 4s1 3d5 instead of 4s2 3d4, because here as the d orbital, in the d level we have these 5 orbitals. So if we have d5, by the promotion of this electron from the s level to the d5, then we have completely half filling of the orbitals, which gives an increasing instability, and that's why this happens. And the energy levels for the levels 4s and 3d are close to each other, so that's why this is possible. So for example, for group 8, then it's 4s2 3d6. So we have the filling of the n-1d orbitals. So here are some examples of the valence electron configuration for several elements here of the D block. So here for the element in the oxidation state 0, in the oxidation state 2, and in the oxidation state 3. So we can see for the oxidation state 2, there is the loss of 2 electrons. That's why here the electrons in the orbital 4s are lost first. And this is then how it is normally the valence electron configurations for the elements in the D block. Okay, in the case of the F block, now we are dealing with the filling of the F orbitals, but the n minus 2 F orbitals, where n here is the period number. Okay, so for example, if we are talking about period 6, then this would be the configuration. N minus 2 F orbitals. So the orbitals 4F are increasingly filled. Okay. All right. So let's talk about now the atomic or the different atomic properties. So this is important because many of the properties of the atoms, they display regular variations that are periodic variations relative to the atomic number. And that's why the periodic table is so useful, because of these regular variations with atomic number. So this, for example, includes the radii or the size of the atoms and the energies that are associated with the removal or the addition of electrons to these atoms. And these properties, like both the size and these kind of energies, they are very important for understanding several chemical properties. Therefore, the knowledge over these trends enables us, or enable chemists and scientists, to rationalize several observations or several experimental observations, and also to predict chemical and structural behavior. So that's why this is so useful. So before we start this discussion on the atomic properties, it is important to understand a concept which is very important, which is the effective nuclear charge, which you also see represented as ZF or Z star, okay? So the effective nuclear charge is defined as the net positive charge that is experienced by an electron in an atom that has several electrons, all right? So it's the net positive charge experienced by an electron in a polyelectronic atom. Why do we say net positive charge or effective positive charge? Effective because in an atom that has several electrons, actually, when we talk about one of the electrons, actually, this electron can experience a shielding effect of the charge that the nucleus operates on this electron. And then this shielding effect comes from the inner negatively charged electrons. So for example, let's take a look at this very simple representation of a polyelectronic atom here. So we have the nucleus here, right, which is positive, and then we have an electron here in this energy level, which is our electron of interest in this case. So all electrons located between the nucleus and this energy level, they also have negative charge because electrons have negative charge, right? And so this means that the positive charge that the nucleus exerts over this electron, or the positive charge that this electron feels coming from the nucleus is smaller because there is some shielding, because there is some electrons in between that also have negative charge and are also feel and are attracted to the nucleus. So these electrons shield this electron of interest by a certain amount. Therefore, this prevents this electron of experiencing the full positive nuclear charge of the nucleus. Therefore, this effective nuclear charge is defined by Z minus S, where Z is the number of the protons in the nucleus, which has positive charges, and S, the shielding constant, which is relative to the number of inner electrons that are present relative to this electron of interest. Was this clear? Okay. Okay, if at any time I'm not clear or something, please feel free to interrupt me and ask questions. All right, so the first atomic properties that we will be discussing are then the atomic and ionic radii. So some key points here that we will learn in this section is that the atomic radius increase down a group. In the S and P blocks, the radius decrease from left to right across a period. An important concept that we will learn in more detail soon is the lanthanoid contraction, and this results in a decrease in the atomic radius for elements following the F block. So it's a decrease in the radius relative to what would be expected based on these periodic trends. Other important concept is that all monoatomic anions are larger than their parent atoms, and all monoatomic cations are smaller. All right. If we talk about the properties of an element, the size of the atoms and the size of the ions can be stated that the size measured by the radius or the radii is probably one of the most useful atomic characteristics of an element, or one of the most useful properties. For example, Size will dictate geometrical considerations, which are important to explain the structure of many solids and many individual molecules. Also, the average distance of an electron from the nucleus of an atom will correlate with the energy that will be needed to remove this electron in the process of forming a cation. And this is important for the formation of compounds, for example. And also, it's important to note that atoms with numerous electrons will tend or are larger than atoms that have only a few electrons, because more electrons will give larger sizes. However, it's important to keep in mind and to understand that when we talk about size of atoms and ions, there is a variety of different definitions of atomic radius that have been proposed, and these variety of definitions come as a result of several empirical considerations. So, for example, one definition is the metallic radius. So the metallic radius refers to the radius or the size of a metallic element. So the metallic radius is defined as half of the experimentally determined distance between the centers of nearest neighbor atoms in the solid. So we have, so for example, if we want to have the radius of iron, for example, so here in the solid, we will have two neighboring atoms of iron, and then we will measure this distance experimentally. Then we can define the metallic radius as this half of the distance that can be experimentally determined. So this would then be this amount, which refers precisely to the radius of the atom. So this is based on the measurement of the solid comprising the metallic element that we are defining. So similarly, we have the definition, or what we call covalent radius, which is now applies, is the same definition, but instead of covering a metal, now it covers a non-metallic element. So this refers, therefore, the covalent radius is of a non-metallic element is similarly defined as half of the internuclear distance between neighboring atoms of the same element in a molecule. So we refer to both the metallic and covalent radii as the atomic radii. So we call like atomic radius when we are talking about both metallic and covalent radius. All right, so atomic radii here in this table or in this figure, and then we can see here how is the variation in atomic radii across the periodic table. So what we can see, for example, when we go down a group, generally what happens is that the atomic radii increases. And when we go from left to right across the periodic table, then what happens is that the atomic radii decreases. Right? Okay, so can anybody explain me why we observe this trend? Okay, let's continue then. All right, so another thing, like if we go to the D block and then we move from left to right along the D block, it gets a little less evident, these variations. So there is a decrease in size, but there are some exceptions here and there. And then in some areas, this decrease in size is not so big. And the same goes when we go down the period here. And we can see that for the second row in the D block to the third period of the D block, the sizes are actually very similar. All right, so as we mentioned, the atomic radii increase down a group, and then they decrease in general from left to right across the periodic table. So we can interpret or explain these trends in terms of the electronic structure of the atoms, right? So when we go down a group, we have more energy levels, more electrons and more energy levels being occupied. So here the electron configurations is for example, is 2s in the second group, in the third group 3s, 4s, and so on, which means that we have more electrons occupying different energy levels, so therefore size increases. But when we go across the same across the same group, but across the period in the periodic table, when we go left to right, there is actually a decrease in the atomic radius, because even though we add more electrons in these atoms in the same period going from left to right, so even though we add more electrons and therefore they have more electrons, and it would be expected that they could be also increasing in size. However, in this case, we have the effective nuclear charge going on. So even though we add more electrons when we go left from right, we also have an increase in the nuclear charge, and therefore the increase in the nuclear charge due to the effective nuclear charge makes this effect is bigger than the increase in size due to the additional electron. Therefore, the size decreases because of the increase in the nuclear charge. And this, therefore, makes the atoms to decrease in size as we go from left to right in the periodic table. Okay, so this was like we discussed the metallic and the covalent radius, which we refer to as the atomic radius. But now let's talk about another definition, which is the ionic radius. So here, the ionic radius, now here, this definition applies to ions, right? Or ionic measurements in ionic compounds. So the ionic radius of an element is related to the distance between the centers of neighboring cations and anions in an ionic compound. So we have an ionic compound with the cation and the anion. So therefore we measure this distance, and from this distance, then we can obtain the ionic radius. However, in this case, we have different elements, right? A different species, a different element for the cation and a different element for the anion. And because of this, we have to make an approximation or an arbitrary decision. So how we can figure out, or how we can estimate or define the atomic or the distances there in a combination of a cation and an anion. In one of the common approximations, we stipulate that the radius of the ion O2- is taken to be 140 picometers. And then therefore the other radius are, or the other radii are defined based relative to this. For example, the ionic radius of magnesium 2 plus, I have sometimes a little trouble and confusion like with manganese and magnesium. You know, I know what they are, but in my head somehow I read magnesium and say manganese sometimes, and the same thing goes all the way around. I see manganese, but I talk magnesium somehow. So I'm sorry if I confuse this, but I will try not to. So magnesium, so the radius of magnesium 2 plus is obtained then by subtracting 140 picometers, which is approximated as the radius of the ion O2 minus from the internuclear distance between adjacent Mg2 plus and O2 2 minus ions in the solid. So this is how we can then stipulate the ionic radii for the other elements. And here we have a table for this, for the variations of the ionic radii for the different cations and anions across the periodic table. All right, so these are the three definitions: metallic radius, covalent radius, so atomic radius, and ionic radius. All right, so here is once more the values for atomic radii for different elements across the periodic table. Now we saw how they change, and then we understood these kind of variations in terms of like down the group and across a period. This is another way to represent these periodic tables in atomic radii, in which we have atomic radii here in the y-axis and atomic number in the x-axis, and here we have the different periods. So from group 1 to group 18 for the different periods. So this is also a nice way to represent. So to summarize, on descending a group, valence electrons are found in orbitals of successively higher energies or higher principal quantum number. So atoms within the group have therefore a greater number of completed shells as we go down. Therefore, the radii normally increase as we go down. Across a period, the valence electrons enters orbitals of the same shell or the same energy level. However, we also have an increase in the effective nuclear charge across the period, that it's a stronger effect and therefore draws in the electrons because of this higher positive nuclear charge, resulting in progressively more compact atoms. So this general increase in the radius down a group and decrease across a period correlates very well with several trends of for many chemical properties. Yeah, and then as we discussed, there is this nice other way to represent these periodic trends. And interestingly, as I also mentioned before, when we talk about the period 6, we have an important modification of these overall or general trends in variation of size. So what happens here in period 6, so this is 2, 3, 4, 5, 6. So what happens here in period 6 is that the metallic radii of the third period of the D block, right? So these we have the D block. So the radii of these elements in this period are very similar to the ones just above. So the elements, the elements in the period 5 and 6, for the D elements have similar radii actually. So the elements, like for the group 6, these metallic radius or radii are not significantly larger as would be expected by the greater number of electrons and going to more and occupying more energy levels, for example, or not larger as expected by these trends that we just discussed. So for example, if we look for the elements molybdenum and tungsten, they have practically very similar or the same atomic radius, despite the fact that tungsten have many more electrons. So this reduction or decrease in the radius or the reduction in the size below of what would be expected based simply on an extrapolation of these periodic trends down the group. So this is called the lanthanoid contraction. So the lanthanoid contraction refers to this decrease in the radius of for these elements below to what would be expected based on the simple extrapolation of this trend that the size increases down a group. Okay, and this happens because if we look here at the periodic table, the elements here, right, which are in this third row, they are preceded by the elements of the first row of the F block, which are the lanthanoids, right? Therefore, for these, in these elements, we have that the 4f orbitals are being occupied. And actually, the problem is that these 4f orbitals, they have very poor shielding properties. Therefore, they are not very effective to shield the outermost electrons in these elements, which means that the valence electrons, they experience a much more attraction from the nuclear charge than what would be expected. And because they experience this larger or more attraction, then the size is reduced. So the element becomes more contracted. So in this case, the repulsions between the electrons being added on crossing the F block, which would give these shielding properties, these repulsions fail to compensate for the increasing nuclear charge. So we have that in practice, the nuclear effective charge increases, and therefore the effect is to draw all the electrons and therefore result in a more compact atom for the later lanthanoids in the third row of the 3 block and the elements that follow them. Okay, so this is another way to represent these variations in atomic radii, in which here the size of the spheres are proportional to the sizes of one of these elements. So here for the main group, and then here for the transition maps. All right, so should we take a break? Do you guys prefer like a 5 or 15-minute break? What's the preference? Or 10 minutes? I think it's good to take a break now, at least 5 minutes. What do you guys think? Okay, yeah, so let's take a 10 minutes break. So let's be back at 1:15, okay? I will see you guys soon. Hello, everyone. So welcome back from our break. So let's continue now our discussion on atomic properties. So after we discussed size, radius, or radii, then we can shift our attention to another very important atomic property, which is the ionization energy, which is also related to the variations in size. So the key points here in this section are that the first ionization energies are lowest at the lowest left of the periodic table, and they are the greatest near the upper right of the periodic table. And successive ionization of species, so successive ionization energies require increasingly larger energies to take place. All right. So what's the definition of ionization energy? So ionization energy refers to the ease with which an electron can be removed from an atom. So this is measured by the ionization energy and can be found with these two kind of nomenclatures. So a more precise definition is that ionization energy refers to the energy needed to remove an electron from a gas phase atom according to this kind of an expression. So refers to the energy of the generated cation relative to the energy of the parent neutral species. So the first ionization energy refers to the energy required to remove the least tightly bounded electron from the neutral atom, so the outermost electron of a neutral atom. Similarly, the second ionization energy, therefore, refers to the energy required to remove the least tightly bound electron from the resulting cation, or the outermost electron of the resulting cation, and so on for the third and so forth. All right, so to a large extent, this first ionization energy of an element is determined by the energy of the highest occupied orbital of its ground state atom. So the ionization energy will be influenced or determined by the energy of the outermost occupied orbital, or the energy of this electron occupies. Therefore, the first ionization energy vary systematically through the periodic table. So here is some data for the first, second, third, and in some cases, fourth ionization energy for the different elements. So here we have the values down a group and across a period. And here is another way to represent these trends for the different periods of the periodic table. So it can be observed that this variation follows the pattern of effective nuclear charge, including like some subtle variations that come from the effect of electron-electron repulsions between the same subshell. So therefore, we can see that this also correlates with the atomic radii, because elements that have small atomic radius have generally high ionization energies. So this is because in a smaller atom, the electron is closer to the nucleus, Therefore, if the electron is closer to the nucleus, it experiences a stronger Coulombic attraction, making it like much harder to remove relative to a larger atom in which the electron therefore will be farther away from the nucleus, experiencing a less pronounced Coulombic attraction. So the atomic radius increases, and therefore the ionization decreases when we go down a group. So as the size increases, therefore ionization energies decrease when we go down a group. We can see here the data for the first ionization energies for the elements in this group, for example. And also across a period, we see a decrease in the radius, as we discussed, and this is reflected as the radius decreased across a period. This means that we have a gradual increase in the ionization energy as we go from left to right in the periodic table. Okay, so here are some ionization energies for some elements. So here we have period 2 of the periodic table, and here we have the first ionization energies for the different elements. We see a gradual increase as we go left and right, and this increase is because size decreases. And therefore, I ask you here an exercise. Explain the variations in the first ionization energies of boron and beryllium, right? Because here we are going left to right. So here we would expect that the ionization energy would increase, but we see a decrease in ionization energy. So I would like you guys to think about it and come up with an explanation together. And so everybody has any ideas? Okay, let me check the chat. Exactly, yeah. We have here the correct answers, in which when we go from beryllium to boron, actually what happens is that when we go to boron, then we go to the p block, right? So the outermost electron occupies a 2p orbital. And this is less strongly bound in the atom relative to the 2s orbital. So it becomes easier to remove this electron. So that's why we have this kind of trend when we compare the beryllium and boron. All right, so if we compare the first, second, and third ionization energies, the successive ionizations of an element require increasingly higher energies. This is because, for example, when we perform the first ionization of the element, the element becomes a cation, so it has a positive charge, and the higher the positive charge of a species, the greater is the electrostatic attraction experienced by the outermost electron. Therefore, this also leads to the electron being more strongly attracted to the nucleus. Therefore, the atom contracts in size is reduced, and this is also as a result of the increased effective nuclear charge. So when we remove an electron, we get positive charge, atom contracts, ionization energies increase. And then we can see this for elements of the different periods. This occurs for all of them. All right, so another exercise, very easy. Which one of these following pairs has the higher first ionization energy? So first, beryllium and boron. So we already discussed this, right? So the higher first ionization energy is beryllium. All right, carbon or silicon? Carbon or silicon? Carbon, because it's smaller. Chromium or manganese? Chromium or manganese? Manganese, right? Because manganese is smaller. All right. A property that is kind of related to ionization energy is the electron affinity. And some key points here regarding electron affinity is that electron affinity is like, or the values for electron affinities are the highest for elements near the fluorine in the periodic table. The electron gain enthalpy referred by this expression is defined as the change in the standard molar enthalpy when a gaseous atom gains an electron. So this is kind of an opposite trend relative to the ionization energy. So the electron gain enthalpy is the change in the molar enthalpy when a gaseous atom gains an electron. Although this electron gain enthalpy is the thermodynamically appropriate term or definition, normally this atomic property is described or discussed in terms of a related property, which is the electron affinity. So the electron affinity in this case is defined as the difference in energy between the gaseous atoms and the gaseous ions at temperature equals 0 Kelvin. So it's the difference in energy for the neutral atom relative to the anion. So in this case, if we have a positive electron affinity, this indicates that the ion has a lower, more negative energy than the neutral atom. So the second electron gain enthalpy, which is the enthalpy change for an attachment of an electron to a mononegatively charged atom, is positive, because in this case, always the electron-electron repulsion outweighs the nuclear attraction. All right, so here we have the electron affinities for the main group elements, right? So here we can observe, like, what's the trend that we can observe here for these electron affinities. So it decreases across the group here, right? So for these elements, we have the highest values of electron affinity. Okay, this will be a good question for homework or for the exam, but this electron affinity is also can be understood or related in terms of electronegativity, which is a very important atomic property as well. So the electronegativity of an element can be defined as the power of an atom of this element to attract electrons when this element is part of a compound. So it's the power of an atom of the element to attract electrons when this element is part of a compound. So we have an increase in electronegativity across the period. So when we go left to right in the periodic table, and a decrease down a group. So this is how it changes. Electronegativity is expressed by this expression in the Greek alphabet. And there is a lot of scales to measure or definitions to measure electronegativity, but all these measurements and definitions are based on atoms in molecules rather than isolated atoms, because the definition of electronegativity refers to the power of an atom to draw or attract electrons when it's part of a compound. And electronegativity actually is a very useful concept when we are trying to rationalize bond energies, types of reactions, prediction of the polarities of the bonds, and prediction of polarities of different molecules. So when we talk about electronegativity, these periodic trends in electronegativity can be predicted by the trends in the size of the atoms and their electron configuration. So this is why size is so important. We saw that size was important for ionization energy, also electron affinity, and also now electronegativity. So if an atom is small and has an almost closed shell of electrons, then it's more likely to have a high electronegativity. Consequently, electronegativities of the elements increase typically from left to right across a period as sizes decrease, and also decrease down a group, because down a group we have an increase in size. And electronegativity is measured like precisely or in quantitative manners by different types of scales. So different types of definitions and scales have been proposed, such as the Pauling electronegativity, the Mulliken electronegativity, and the Alfred Huckel electronegativity. So in the case of Pauling definition of electronegativity, we will not go into details of these definitions, but the Pauling definition draws on concepts related to the energetics of bond formation. The definition of Mulliken states that if an atom has a high ionization energy and high electron affinity, it will be likely to acquire rather than lose electrons when it's part of the compound. So we have this kind of formula relating to ionization energy and electron affinity. And Alfred Huckel is a more complicated definition in which electronegativity is determined by the electric field at the surface of the atom according to this kind of equation. Okay, so here are the values for electronegativity for these different kinds of definitions. So we can see the variations here down the group in which we have an increase in size. So down the group, we have the increase in size, therefore decreasing electronegativity, and across a period, decrease in size, and therefore increase in electronegativity. And this can be also expressed by this kind of diagrams as well, which makes it very clear. And here we also have this representation with the values of electronegativity for the different elements. So here I believe we are referring to the Pauling electronegativity in this case. All right, so which one of the following pairs is more electronegative? Sodium or cesium? Sodium, yes, because it's smaller in size. Silicium or oxygen? Oxygen, yes, because oxygen is smaller. Good, thank you very much, Aaron. Good job. Another important atomic property is the polarizability, which refers to, which is defined as the polarizability of an atom is defined as the ability of this atom to be distorted by an electric field, such as a neighboring ion. So it's the ability of this atom to be distorted by a neighboring atom. So if an atom is highly polarizable, it means that the electron distribution can be distorted readily or easily. And this is most likely to occur if we have large anions with low charge density and low effective nuclear charge, so that the electrons, the outermost electrons, are less tightly bound to the nucleus. So, and the species that can effectively distort the electron distribution of a neighboring atom or anion are therefore described as having polarizing ability. So these are typically small or highly charged cations with a high charge density. So regarding polarizability, we have Farhan rules that summarizes the factors that affect polarization. So according to these rules, small, highly charged cations have polarizing ability. Large, highly charged anions are easy polarized, and cations that do not have a noble gas electron configuration are easily polarized. Okay, or easily polarized. So small, highly charged cations have polarizing ability, so cations are always smaller than the parent neutral atoms. Large charged anions are easy polarized because they are bigger. Anions are always bigger than the parent atom, and cations that don't have noble gas configuration are easily polarized. All right, another important property is the enthalpy of atomization. So the enthalpy of atomization of an element is a measure of the energy required to form gaseous atoms of a species. So for example, if we are talking about solids, the atomization enthalpy is the enthalpy change associated with the atomization of the solid. For molecular species, this refers to the enthalpy of dissociation of the molecules. So regarding the variations in the enthalpy of atomization across the periodic table, it first increases and then decreases across periods 2 and 3, reaching a maximum for carbon in period 2 and silicon and silicium in period 3. Okay, so these are the values for the enthalpy of atomization. And here are the variations as we go like across the different groups. Here we are in a period across the different groups. So here in blue, we have the variation for period 2, and here in red, the variation for period 3. So, okay, so in general, when we go down a group, the enthalpy of atomization decreases. This is because atoms get bigger, so it's easy. So if atoms are bigger, the distance between the bonds of these atoms, are larger, so they are easier to break. So the enthalpy of atomization decreases. And across a period, we have an increase. So if you look here at period 2, it increases until carbon, and then after carbon, there is a decrease. So if we compare the enthalpy of atomization for the D block relative to the S and the P block, we can see that for the D block, these enthalpies of atomization are higher, and this is because we have more valence electrons occupying the D orbitals for these D block elements. So if we have this greater number of electrons, this means that they can participate to create stronger bonding. Therefore, these atomization enthalpies for the D block are usually higher as a result of the stronger bonding, which occur as a result of this higher number of valence electrons. The enthalpy of atomization, so in the S and P blocks, they decrease down a group, as I mentioned, as sizes increase. So these in the S and the P blocks. But when we are talking in the D block, actually the enthalpy of atomization increases when we go down a group. And this is because also of a stronger bonding in these elements of the D block. So therefore, S and P orbitals become less effective at forming bonds as the period number increases or as we go down a group, while the D orbitals become more effective at forming bonds as we go down a group. And this can be explained by the way or the configurations of these different orbitals. So the expansion of the p orbitals on descending a group from they become far from optimum to overlap or too diffuse to extensively overlap with each other. Therefore, this leads to weaker bonding between these elements. And in contrast, as the d orbitals expand in size, they change from too contracted to optimum for overlap. So they become more effective to create bonding between these elements of same identity. So that's why we have these differences in these trends for the enthalpy of atomization. This refers to the trends in bonding that these elements can make with each other. So for D block, as sizes get larger and D orbitals more external, they can overlap better with each other. While for the S and P block, the trend is the opposite. So larger, more diffuse S and P orbitals, the bonds on the overlap as we go down a group become less and less effective. All right, we can also predict how the occurrence of the different elements based on the regions in which they are on the periodic table. So we can also see a kind of a periodic trend or a periodic variation on how the different elements located in different regions of the periodic table occur in nature. And in this context, the concept of hard and soft interactions is useful and helps us to systemize or to systematically understand this terrestrial distribution of the different elements. So these hard and soft interactions are usually described in terms of the HSAB theory, which is hard and soft acids and bases. So hard and soft acids and bases in the definition of Lewis definitions of acids and bases. So this is known as the Pearson's acid-base concept. So we are not gonna go into much details here now, but in this concept, in this definition, we can define acids and bases as being either hard or soft. So we assign terms hard or soft to a species or acid and base. So we classify the species as an acid or as a base, and an acid can be a hard or soft acid, and a base can be a hard and soft base. And in this case, a hard species applies to a species that is small, have high charge states, and are weakly polarizable. While soft applies to species that are big, have low charge states, and are strongly polarizable. So here, according to this framework, then this concept means that like soft species tend to bind to soft species, or soft species form species that are more energetically favorable or more stable with soft species, and hard species tend to bind to hard species or tend to form more stable compounds with hard species. So this is soft and hard interactions. So soft and hard interactions are favorable. So this helps us therefore to rationalize the type of compound that element forms in nature. Therefore, as I said, soft acids tend to bond to soft bases, and hard acids to hard bases. So here we have the different elements in the periodic table. So here we can approach these species as being, for example, Lewis acids, and these species as being Lewis bases. So for example, here, these species are classified as hard, the species here in yellow as intermediate, and the species in blue are soft, and the same here for the bases. Orange, hard, yellow, intermediate, and blue, soft. It's important to note that these definitions from this Pearson's theory of soft and hard and soft acids and bases, this is a classification that was determined totally experimentally. So this comes from experimental observations by measuring the thermodynamic stability of compounds with different species. So this is a scale based on experimental measurements. So that's how these definitions were done. And these trends in soft and hard interactions explain some aspects of the Goldsmith classification of the elements into 4 types, which is widely used in geochemistry. So for example, lithophiles are the compounds or elements found primarily in the Earth crust, the lithosphere, in silicate minerals, and include lithium, magnesium, titanium, aluminum, and chromium as their cations. So these cations are hard, and therefore they are found in association with a hard base, oxygen, The chalcophiles are often found in combination with sulfide and selenide and pteroline, and these include cadmium, lead, and bismuth. Bismuth, for example, these elements are soft, and then they are associated with the soft bases. In the case of zinc, zinc are borderline hard, but it's softer than aluminum and chromium, and zinc therefore can also be found as the sulfide. Like we have also the siderophiles that are intermediate in terms of hardness and softness and show affinity for both oxygen and sulfur. They occur mainly in their elemental state, including like some metals, and the atmophiles, that are elements that occur as gases, and such as hydrogen, nitrogen, and the group 18 elements. So for the siderophiles, chalcophiles, and lithophiles, these hard, soft interactions help us to rationalize their occurrence in nature. And here is a table showing, like describing the different elements within these frameworks: lithophiles, siderophiles, chalcophiles, and atmophiles. Okay, so I think we have covered enough for today. So next class on Monday, we will discuss a little more of these properties regarding the properties of the atoms across the periodic table. We will discuss oxidation states, metallic character, coordination number, bond enthalpy trends, and then some binary compounds as well, or several binary compounds. But I think today we have discussed enough, and then we are reaching the end of our class. So it was, does anybody have any questions before we go?
Yes, I just wanted to ask, because on CISO we have a class on a Friday.
Yes.
Yes, but you, okay, never mind.
Yeah, we have class on Friday, right? It's Mondays and Fridays, this class, right?
Yeah. Okay, sorry for the confusion.
Okay, no problem. Yeah, guys, and also I forgot to mention here in the first slide. So my office is in Chemicon, 3rd floor, room 326. So please feel free to contact me or stop by if you have any questions or anything regarding the lectures. Okay, I will post these slides and the video of the lectures later today or early tomorrow on Moodle for you guys to have fun and watch it again. And I will put this file on Moodle very soon or right now, so that you guys already have the materials, and then I'll put the lectures there as well. So I'm gonna do that now to make these slides available for you, okay? So if no other questions, I will see you guys then on Friday. All right? Bye-bye, everyone.